it's private. Manage streams. Manage. PhD defense. Edit. Unlisted. Save. Okay. PhD defense. Live. Okay, let's send this link to my mum. Skype. Jesus Christ. Call my mum. Oh jeez, this is going to be terrible actually. That's a bad idea. I have to call her on my phone because the microphone is really close. Okay, it doesn't matter. Yeah, Alex will probably sit here and make sure that's okay. Okay, it's coming together more or less. All the electronics. Okay, 12% on my thing. This is excellent. 12% is a shitload of jobs. 12% is like crazy. Oh, I didn't sleep very well. I slept very badly.
It's okay.
Should be fine.
You'll do fine, you'll do.
People listen to me. What the fuck is that? No, stupid stuff is happening. Okay, let's call my mom. Thanks, Aditya, for coming out.
Shall I bring the food?
No, food is after, Jesus Christ.
Food after.
Oh, you think it's like a movie?
Oh yeah, that's right.
I think people are... Jesus Christ. Okay, my mom doesn't want to talk to me. Okay, I don't care about it. I'm going to talk to my father instead. Oh. Turn down the... Oh, wait. Алло? Ну, короче, да, пиздец. Ему просто плевать. Это. Okay, they can go to hell now. I've sent them all the thing, I've done everything in my power. They don't want to talk to me. Okay, I'm not going to talk to them either. Ah, that's excellent. Yeah, Aditya, have a look how terrible this is. Oh, sorry. Oh, Ashley.
Are you Aditya? You're not.
No, this is Alex.
Hi, Alex. I'm Alex. I'm Ashley. Hi, Ashley. I don't think this is good. It's okay. I'll try.
This is all terrible. Can you see how it looks on the camera? Is it like readable?
You have a call.
It's pretty bad, isn't it? How's it that bad?
You have a call.
Oh, Jesus Christ. Okay. Oh, shit. Never mind.
Well, I mean, there's a delay, but it's okay.
No. There's a... Oh, it's going to be really bad now.
Yeah, there it goes.
Okay, let's call my mom. One of you needs to be in charge of this camera, and like, it's really bad quality, but you have to like do your best. It shouldn't be that white though. It should be at least readable. Okay, my mom's been talking to me.
Well, where are the camera settings? We can probably reduce the contrast and all that.
Oh, do you know how to do that?
Well, I mean, we
Are
need
you
to
right?
access them on the computer.
How the hell do you do this? Yeah. Camera. I tried this actually.
Where's the software that this comes with?
I just plugged it in and it was fine.
Hmm.
Okay, don't, it's too late. It's too late.
Let me try something. Let's see. Which one of these looks like the camera?
What the hell is that NG thing? Jesus Christ. What the hell is this? Oh, okay. Oh, that doesn't do anything. Oh, there, look, it's good.
Oh, good.
Don't touch it. There, you can actually read some of it. Okay. Алло? Привет, мам, все слышно? Да, мам, там как со звуком?
He's live streaming it to YouTube right now.
Скопируй, мам, и... Хорошо, мне главное звук понять, как там это...
Very good.
Херовый он или более-менее нормальный?
Is this auto adjusting or not? That's good. Okay.
Главное, чтобы не было feedback loop. Слышишь? Ты слышишь меня? Ты меня видишь? Хорошо, слава богу, более-менее нормально, да? Ну я вышел с ним. Все отлично, да? Хорошо, спасибо, да. Хорошо, пока. Okay, excellent.
Well, the sound is working on this, right?
Yeah, the sound is working.
Good.
Okay. Let's do this. 10 minutes. Okay. Almost set up. I have to just call my supervisors. Oh, Jesus Christ. Terrible.
You need a bottle of water or something? Might help you calm down.
No, it'll be alright. It'll be good.
Do you want tea?
Tea is good.
Yeah, well, that would be nice. Okay, thanks, Eddie.
Okay. I don't have the key to that room. This is in your office, right? Okay.
Connection is too weak. Oh, is it really? Oh yeah, I haven't signed in. Okay, let's try to talk to them via Skype. That time is wrong. I still have 10 minutes.
How's that time wrong?
This computer has not been used in like 2 weeks.
Oh man.
I hate this computer. Well, I like it, but it's just starting
To die.
Yeah, it's starting to screw up. It's starting to be all these stupid bugs.
Did you do a full system update recently?
I don't know. I don't know what I did. It has its own model. It doesn't want to. It doesn't want to do it. Oh god, that is terrible video quality.
trying to reach is currently unavailable. Please leave a message after the beep.
А, there it is. Алло? Здравствуйте.
Здрасте. Ну что?
Сейчас я камеру. Вы ничего не видите, да? Камера.
Ну, пока что ничего не вижу.
Сейчас я вам перезвоню тогда. Алло? Алло, вы слышите меня? Алло? Алло?
Да, ну я вижу что-то, но очень...
Очень хреново, да?
Да.
Да, это действительно чересчур. Очень плохо.
Ладно, звук будет слышно, а чего там еще?
Хорошо.
Это далеко от экрана стоит все.
Нет, это довольно близко, но он же все-таки подсоединен к этому. Но с другой стороны вы видите более-менее. Сейчас.
Что-нибудь я увижу и все.
Хорошо, спасибо большое. Такое надо супер важно. Кстати, можно еще совместно поговорить с этим, с Магазеевым?
Ну, пожалуйста, нажми плюс и вызывай Магазеева.
Давайте. Где это плюс?
Наверху экрана.
Нет.
Там человечек и плюс.
Я вижу, да. Давайте. Сейчас, у меня вообще он есть? Давайте попробуем его найти.
Ну там должен тебе меню давать. Ты набираешь?
Да, я знаю. Мне, наверное, просто нужно найти сначала Магазеева.
Хорошо, не надо искать. Ты набираешь этот плюс. Она тебе выдает add to call. И там search есть. Перепишешь Магазеев и все.
Есть. Отлично. Все, он сейчас...
4 минуты осталось, 4 минуты осталось. И так что...
Он что-то получается или...
Я не знаю, ты его вызвал?
Вроде бы вызвал.
Да, вот он подсоединился.
Он может что-то сказать или...
А зачем ему говорить? Мы будем молчать, мы будем смотреть. Или мы должны говорить?
Не. Хорошо. Попробуем. Что здесь мигает? Херня. Ну хорошо. Давайте попробуем.
Нет, начинаем уже, там 3 минуты осталось. Оставьте компьютер.
Никого вообще нету на самом деле. То есть там вообще никого нет.
Он подсоединился, Магазеев подсоединился.
Хорошо. Yes?
Да,
вы здесь?
Мне прямо телефон звонит, у меня будет плохая связь, это плохая идея. К чему на телефон, да? Ну ты смотреть можешь, смотри на телефон, так и все. Я что-то вижу, но у меня тут отсюда, надо было раньше говорить, у меня телефонная связь плохая здесь.
Вы ему дома или вы можете на компьютер? Я могу вам перезвонить просто?
Ой, ну мне надо тогда лэптоп. Я не знаю, через что? Я не знаю, на компьютер. Это что у нас? Это у нас... Ну, я понял, да. Сейчас, я думаю, Наверное, да, сейчас тогда надо как-то через компьютер, я попробую соединиться.
Хорошо, я тогда...
Ладно, ты отсоединил, я потом сам подсоединю.
Хорошо, вы сами тогда, да, отлично, да.
Да.
Хорошо, я попробую все-таки с компьютером что-то сделать, чтобы хотя бы немножко лучше было.
Подальше его надо, понимаешь, если ты будешь ходить перед компьютером, ты закрываешь камеру, и экран становится ярким. А если ты уйдешь от компьютера, то будет нормально все.
А, хорошо. Вот
Не
так
надо
вот.
закрывать его. Тогда он настроит яркость.
Хорошо. Нужно свет немножко включить тоже чуть-чуть, наверное. It's usually not this dark, right? Is it that light? That's okay, right?
You want these lights?
How dark is it supposed to be? Yeah, this is okay, right? What's this camera? Oh, let's not worry. Yeah, Alex, can you look?
Yeah, I'll be right here.
Do your best with it.
Yeah, I think it'll be okay.
Okay,
So I'll just, yeah.
this seems to work. Okay. This computer thing seems to be okay. Seems to be working slightly. Oh, Jesus Christ, it's not charging.
Я не понимаю, почему так происходит.
А что там?
А зачем идет еще на это? На экран идет скайп.
Ну это я просто хочу посмотреть.
Мне на экран. Скайп на экран не должен идти. Он должен только нам идти. А на экран проектора не скайп не должен идти.
Хорошо. Ну это какие-то сеттингсы нужно, чтобы там сделать.
Надо скайп с одного компьютера, а доклад на другом было делать.
Да, хорошо, наверное, да.
I think it's something to do with the connection. The connection is loose.
Ну так еще ничего. Ну вот это вот зачем? Вот это.
Maybe members aren't here, so I still have time.
Yeah, I think it would be better if we change the laptop.
Yeah.
Yeah.
Alex, can I change
Yeah.
the laptop for yours? It's charging actually. Oh, okay, it's fine.
It's fine.
Yeah, it's fine.
Okay.
Let's hope it stays the same. View full screen. It's still charging? It's not lying to us. Все видно, да? Нормально, более-менее. Алло?
Да.
Хорошо, вы добавите туда Магазеева и это. Хорошо, спасибо большое. Кто? Да, он есть. Юзбашан, да? We're just waiting for Юзбашан. Okay, this is working. Let's look on the camera. Ashley. Let's look on the- There'll be food afterwards as well. So. And
Ну что ты сдвинул сильно? Ты направь камеру на экран.
куда? Направо, налево сдвинуть? Я честно, вот так вот? Лучше?
Нет, в другую сторону.
Вот так?
Да, вот так.
Нормально?
Ну ладно, так лучше. Все. Ну там full screen ты сделай.
Да, сейчас сделаю full screen. seems to be.
Sure. Finish.
Well, Sebastian.
So everybody can, so we can start.
We can start. Okay. So thank you very much, all of you, for coming. Today I'm going to be talking about my research on the quantization of integrable signal models, which I did under the supervision of Professor Luciano. So integrability is sort of an important but specialized topic in mathematical physics. And so I thought I'd start by giving some background to what integrability is. So the concept has its roots in classical mechanics, and many famous problems in this area, such as the Kepler problem of planetary motion, for example, is exactly soluble, is integrable. It was realized at the end of the 19th century that integrability is, solubility is closely connected with the presence of a sufficient number of integrals of motion in the theory that allow the differential equations to be integrated. And this led to the notion of a Liouville integrable system. So a system is Liouville integrable if the number of functionally independent Poisson commuting integrals of motion is equal to the number of degrees of freedom in the system. And it was proved that for a Liouville integrable system, the equations of motion can be solved in quadratures. So just to illustrate this concept, let's give a simple example, that of the free top. And for the case of the free top, the center of mass, the motion of the center of mass is trivial. And so that we only have to worry about the rotation of the rigid body. And a convenient way to describe the rotation is to introduce a fixed frame, which is fixed inside the rigid body. And then the rotation can be described by a rotation matrix that relates the orientation of the fixed frame, of the frame fixed to the body with a laboratory frame. Thus, the configuration space is the space of rotation matrices, SO3, and because it takes free parameters to describe a rotation, the number of degrees of freedom is free. And this system has three integrals of motion in involution. One is the Hamiltonian, the other is the projection of angular momentum along the laboratory frame EZ, and the third one can be taken to be the projection of the angular momentum along E3 prime. Can you hear everything? Hello? Okay, I think you can hear. Okay, that's excellent. We'll assume you can hear. So the notion of Liouville integrability, however, fails for, or doesn't work for systems with an infinite number of degrees of freedom, such as a partial differential equation. And it's difficult to assign a precise meaning of integrability in this context. However, an idea came from the study of, from the theory of solitons. And a soliton is a stationary wave that doesn't, is a wave, solitary wave that doesn't change its form and moves without dispersion. And the first time Russell saw a soliton, he saw it in a narrow canal, it blew his mind. And he followed it on horseback for 1 to 2 miles before he got lost in the other waves. And at the end of the 19th century, this partial differential equation was introduced to describe these solitons by Korteweg de Vries. And the study of this partial differential equation proved to be extremely fruitful. So it was solved in '67 by an ingenious method based on the scattering problem for the one-dimensional stationary Schrödinger equation. And in 1968, the solution was generalized to other partial differential equations. And the end result of this work was the formulation of the inverse scattering transform method for the solution of a certain class of integral partial differential equation in 1+1 dimensions. And it's a very useful paradigm of integrability, but it's definitely not the full picture. So the key ingredient in the modern formulation of the inverse scattering transform is the zero curvature representation for the classical equations of motion. So this here can be thought of as a matrix, or more precisely, it has to be, to make sense of this commutator, it has to be Lie algebra valued. And it's important that it depends on this spectral parameter lambda. Now, if this is equal to 0 as a consequence of the equations of motion, it follows that the Wilson loops remain unchanged under continuous deformations of the contour C. So in this example, we can move the contour up and down the cylinder without changing T of lambda. And this implies that T of lambda is a conserved quantity. And in fact, it's not just one conserved quantity. Because of this dependence on the spectral parameter lambda, it generates an infinite family of integrals of motion. So let me just give you a simple example, and this example actually sort of builds on the previous example I showed you, the Euler top. I'm going to talk about the principal chiral field for a bit, which is sort of can be thought of as a field theory generalization of the spherical top. So in order to introduce it, let's start with the spherical top Lagrangian, and here it's just the same as the total angular momentum squared, and it's given by this expression. And recall that the orientation of the rigid body is specified by this rotation matrix U. And in terms of this, the angular momentum can be written in this form. So this means that the Lagrangian can be rewritten as here, solely in terms of this rotation matrix U. And this Lagrangian admits an important interpretation of a particle moving on the group manifold of SO3. And it's well known that the group manifold of SO3 is just the free sphere with antipodal points identified. In fact, for our purposes, it's more what we'll need is the particle moving on S3, on the free sphere rather than SO3. So we'll take this matrix U to be an element of SU2. One can't hear. I can hear, but I don't have a picture.
Everything's okay.
Stop?
Everything is okay. Continue.
Oh, everything's okay. Okay, all right. Okay, sorry about this. So this Lagrangian can be interpreted as the Lagrangian describing a free particle moving on the free sphere. And in coordinates, if I were to write in coordinates given by this expression, where GAB is just the usual round metric on the sphere. Now, the Lagrangian on the previous slide admits an immediate field theory generalization where we take this matrix U to depend on X as well as T. So it's a field now, taking values in SU2. And heuristically, this can be thought of rather than a particle moving on a free sphere, this is a string moving on the three-dimensional sphere. And here I've drawn the two-dimensional sphere, but it's on a three-dimensional one. Now the equations, the Euler-Lagrange equations for this model are just given here. And you can check by direct calculation that if you choose the connection in this way, where lambda can be anything you like, then the equations of motion imply that this combination is equal to 0. Now, as in Liouville integrability, it's natural to expect that for integrability 1 plus 1 dimensional field theory, an important condition is that the conserved charges Poisson commute. And this sort of boils down to showing a relation like this, that the Wilson loop, which generates the conserved charges, commutes with different values of the spectral parameter. And in general, these relations are entirely not obvious. However, an idea of how to, say, prove them or see them came from a completely different field in physics. It came from the field of exactly soluble 2D lattice models. So these pioneering works led to the discovery of the Yang-Baxter algebras, which are closely tied to integrability now, and they also inspired many developments in mathematics, such as quantum groups, also developments in geometry and topology, combinatorics, and representation theory. So here I'm going to briefly try to describe in one slide what the Yang-Baxter algebras are in 2D lattice systems. Just to give you an idea of what these things are about. So in 2D lattice systems, we usually study a model such as a vertex model that's given here. So this vertex model is formulated on a square lattice, and it contains these vertices. And I know the picture is small. It contains these vertices, and so these vertices, they have different types, and they're distinguished by the configurations of arrows around the vertices. So, for example, this vertex is different to this one because the arrows around it on the neighboring edges are different. And to each type of vertex, you associate some energy. And the problem is to compute the partition function, which is just the sum of the configurations over all of these possible combinations of vertices for the lattice, such that the Boltzmann weight of the lattice is given as the product of the local Boltzmann weights. Now, integrability in this context is encoded in this relation here, where R is a matrix built from the Boltzmann weights, which are all parameterized by lambda. And pictorially, it can be represented by this figure. So what this figure represents is that you can take this line and you can move it towards this vertex, and you can move it past this vertex and put it on this side, and then you end up with this picture. And this equation means that says that these two configurations are identical. So now let's have a look at the picture on the left-hand side of this slide. So if you have a relation that, such as this one, that holds such as this one, it means that you can take each one of these lines and push it past this vertex onto the other side. And if you do it for every single one of these lines, you end up with a picture on the right-hand side. So mathematically what this means is that this sort of local relation implies this Yang-Baxter algebra, where M is known as the Monodrory matrix, and it sort of heuristically corresponds to a single row of the lattice. Now, you can see immediately that if you have something like this, it follows that T of lambda, which is the trace of this monodromy, commutes for different values of the spectral parameter. And in 2D lattice systems, this is an extremely important condition. It greatly simplifies having such a large quantity of commuting operators greatly simplifies the eigenvalue problem for T of lambda. And since the partition function can be written in terms of these eigenvalues, it enables the computation of the partition function, at least in the thermodynamic limit. Now, let's for a moment consider this as a formal algebra for the matrix elements of M that define their commutation relations. And let's suppose that you can take some classical limit.
So I'm confused about something. So M is in the endomorphisms of V for some vector space V. Is R in the endomorphisms of V tensor V? Or?
So R is in the endomorphism of V tensor V, whereas M is in the endomorphism of n copies of V. So these n's are...
No, well, let's see. Let's see. R is in endomorphisms of V tensor V. Then isn't M also in the endomorphisms of V tensor V?
So the multiplication... So these labels 1, 2, 1, 3, 2, 3.
Right, so that's
label the
so
vector
you have
spaces.
V1 tensor V2 tensor V3. But let's see. So R is in the endomorphisms of V tensor V.
Yes.
So M is therefore also in the.
So
it's in the endomorphisms of V1 tensor Vn.
Yes.
I see, yeah.
Yeah, so you do the multiplication on the first space,
Yeah.
and you leave the other one.
So let's see. So in this line down here, where do these things come? So M lambda 1 is in the endomorphisms of V1 tensor ... tensor Vn, and where does M of lambda 2 live?
Okay,
Another copy of V1 tensor.
Let me. This is very heuristic. I agree, and let me make this more precise. So in this multiplication, you're multiplying over something called the auxiliary space, which is given by the first index in these R matrices. So this M is in the endomorphism of V cross n copies of V. And the first V is called the auxiliary space, and the n copies are called the physical space. And this tensor product here is over the auxiliary space. And this R lives fully in terms of the auxiliary space. So in this, let's imagine this equation. M is a matrix So let's imagine this equation as specifying the commutational relations of the matrix elements of M. So M is a matrix in the auxiliary space, but its entries are sort of operators in some sense. It's an operator value matrix. And this sort of specifies their commutation relations. Now, let's suppose we can take the classical limit of this algebra. And we take it in the usual sense, and also we assume that the numerical matrix R has this low small h bar behavior. Then it follows that this relation becomes this Poisson bracket algebra, where the entries of M are no longer operators but are functions. Now it was realized, it was found by Sklyanin by the study of some explicit examples, such as the nonlinear Schrödinger equation, which is a integrable partial differential equation, that the monodromy matrix defined is just the same as the Wilson loop but without taking the trace, actually satisfies this Poisson algebra. And if this is, notice that if this is the case, then just by taking the trace of the auxiliary space on both sides of this equation immediately implies the desired Poisson commutativity conditions. So how can we sort of imagine, so these are called the scaling exchange relations as well. So how can we imagine these sort of relations, these scaling exchange relations, to appear in a classical integrable field theory? Well, it's sort of inspired by the lattice case. We can take an approach based on discretization, where we take this contour and we discretize it onto n segments. Then the monodromy matrix can be written as the ordered product of these elementary transport matrices, which correspond to the half order exponential of A just over a single one of these segments. And in order to have something like the scaling exchange relations in your theory, you would need these Poisson brackets to Poisson commute for different segments, while for the same segment they have to form sort of a similar algebra. And then the scaling relations immediately follow from this for the full monodromy matrix. And this is similar to the sort of lattice derivation that I gave before. Now, the continual limit of the Dirac of this delta is just obviously the Dirac delta function. And in fact, this relations would follow if the connection here satisfies its ultralocal relations. Now, this interchange of ideas between 2D lattice models and 1 + 1 dimensional integral partial differential equations was extremely fruitful, and it led to the development of the so-called quantum inverse scattering method, for the quantization, which is a systematic and unified approach for the quantization of an integrable field theory. So in the quantum inverse scattering method, the logic that we just went through is sort of reversed. So we start with some integrable field theory, which has a Lagrangian, and the Poisson brackets are just the ones that are induced from the Lagrangian, and we take the connection and we compute the Poisson brackets, and we find that they satisfy this relation. From this, we immediately get this one, and then we get the scaling exchange relations. Now at this point there's some postulate, and the postulate is that similar to the correspondence principle between a classical mechanics system and a quantum mechanics system, where the Poisson brackets are replaced by commutators, in an integrable field theory we replace this Poisson algebra by this Young-Baxter algebra. And this immediately implies that the quantum version of the Wilson loops, they're called the quantum transfer matrices, form a commuting family in the quantum integrable field theory, which sort of enables its solution. Now the most difficult step in all of this is to construct a suitable representation of this Young-Baxter algebra. And the usual method, and the common approach that this is done, is based on discretization. So we take these relations with the elementary transport matrices, and we quantize them instead, and then if they admit a finite dimensional representation, the discretized quantum system can be interpreted as an exactly solvable 2D lattice model, whose solution can be obtained using the Bethe-Ansatz. And the solution of the continuous quantum field theory is achieved by taking the appropriate scaling limit. And these ideas were extremely successful for a number of models, such as the nonlinear Schrödinger equation, the Sine-Gordon model. However, the QISM sort of fails immediately for large parts of theories, such as the SU2 principal chiral field. And the reason this is the case is that the Poisson brackets of this induced from the Lagrangian don't have the ultralocal form. they have this extra term proportional to the derivative of the delta function. And it follows by direct computation that the Poisson brackets of the elementary transport matrix no longer commute for different segments. So if n is adjacent to m, this picks up a contact term from the integral of the delta function. Now, in order to handle such contact terms, you need some sort of regularization procedure. And it turns out that further computations depend on the regularization procedure you chose, and they're somewhat non-universal. And this creates problems in derivations of Scalian relations. Now, an alternative approach an approach was developed by Maillet, where he introduced some sort of regularization procedure and proceeded to compute the Poisson brackets of the Monodromy matrix. But he did not obtain the Scalian relations. The relations he obtained were modified, and it's not understood how to quantize these modified relations that he obtained, and how to proceed with the quantization.
So can you go in reverse, meaning like if you have a quantum integrable model, can you always construct a corresponding classical model?
I mean, you're asking if you can take the classical limit.
Yes.
Well, I think for most models you can do that. Do you have any specific?
Like, for example, Hubbard model.
Well, Hubbard is a spin chain. So it's not a quantum field theory. It could be described by a quantum field theory in the continuous limit, so the scaling behavior might be described by quantum field theory, and you could take the classical limit of that. But the Hubbard model is a many-body system.
I thought it's a fermion model.
But isn't it fermions on a site?
Yes, it's a lattice model.
It's a lattice
definitely.
model.
Yeah, but I thought you had lattice model in your construction too.
So this was inspired by lattice models are very useful and important tools, and this whole thing was inspired by lattice models. But this only works for integrable quantum field theory. Lattice models can be viewed as sort of as a lattice regularization of a quantum field theory in that sense. But you take the classical limit of the QFT.
And if it's a field theory, so can you always have a classical limit? Like it's an integrable field theory. Do you always have an integrable classical?
Well, I mean, say for example, conformal field theory. So I'm not sure that's the case. Where you don't have a Lagrangian, for example. I'm not sure how that could be done, but for the models we'll be considering, you can take the classical limit. We're interested in the sort of first principle quantization of classical field theory. So in our case, there's always this relation.
Well, you're going from classical to quant.
Yes, we're going from classical to quant.
Yeah, so of course, I mean, if you have that root, always you can do it. I mean,
yeah,
there's the classical limit.
Mm-hmm.
But I was wondering if there are cases when there is a integral quantum field theory which doesn't have a clear, like unique classical integrable limit.
I mean, I don't know any examples off the top of my head.
About Ising model. If you think it's just not a Grassmannian numbers, right? Ising model, isolated point.
Right.
There's no classical in the
Right,
sense.
right.
That was clear.
Yeah, I mean, that's why I mentioned Hubbard, because it's like
fermion. Yeah, certainly. So you can have a scaling limit, but not a usual sense classical. Here you need the one constant continuous parameters.
Mm-hmm. Okay. So there were some early attempts at the quantization of the ON models, and these are sort of the field theory equivalents of a particle moving on an n-1 sphere. And in particular, say the O4 model is the same as the SU2 principal Karak field. So Polyakov studied these ON models in '77, and he found strong evidence to suggest their quantum integrability because he found lots of commuting operators. And then this was used by Zamolodchikov and Zamolodchikov they use this knowledge to construct the exact to propose the exact S metrics for the theory. Then Polyakov and Bigman, and later Faddeev and Shatikhin, attempted to quantize the O4 sigma model. And what they did in both works, they just replaced the model by a different one that satisfies the ultra-locality condition, and then quantized that instead. And then they gained valuable results about the non-ultra-local O4 model for a certain limiting procedure. Right, and although these are very impressive results, unfortunately, it's difficult to imagine that this could be used as the basis of a systematic and unified approach to the quantization of non-ultra-local models. First of all, it's unclear whether it can be applied to other cases or whether even other observables in the O4 model, the same limit can be taken. Other observables for the O4 model can be obtained in the same way if we're taking some limit. And so in the past 30 years, there's been no systematic approach to the quantization of integral non-ultra-local models. And say, for example, even for these simple cases like the O3 and the O4 models, the construction and computation of the spectrum of the quantum transfer matrices has remained an open problem. Now at this point, given that this problem is so difficult, we could always sort of give up and move on to something else and forget about all of this. Or at the very least, we need a very strong motivation to want to sort of study these field theories. And if there is strong motivation, we also need some sort of new tools and new methods that will enable us to make some progress, because otherwise we'll be just stuck where these other people were stuck. So let's first of all try to answer this question one. Is it worth trying to continue trying to quantize these models? In order to answer this question, let's go back to why these models were originally studied in the first place. And the reason is that ON models are sort of our interesting playground where you can study a whole range of QFT phenomena, such as instantons and asymptotic freedoms, in a simpler context. Moreover, there's a generalization, sort of can be thought of as a generalization of these ON models, these more general models called these nonlinear sigma models. And in the simplest setup, the Lagrangian has this form where X take values in some sort of manifold, and G is the metric tensor for the manifold. And this class of theories is also non-ultra-local, and they have typically the same problems for their quantization. And also they have many interesting applications. The first of all in string theory, in mathematics, in condensed matter physics, they're used to model disordered electronic systems. And perhaps one of the main motivations is that very recently, integrability has been used to study the ADS-CFT correspondence. And these integrable nonlinear sigma models also appear in this context. So the motivations seem to be strong. So now let's ask the question, do we have some new approach, some new method that can help us make progress? And in fact, the new approach to integrable QFT has been developed in the past 30 years, and it's based on this discovery of the ODI QFT correspondence. So first of all, in these works by Bajanov, Lukyanov, Zamal-Lotchikov, it was demonstrated that in the case of integrable conformal field theories, these quantum transfer matrices can be constructed directly in the Hilbert space without any sort of discretization procedure. Then it was realized that sort of many deep connections between these representations of the Yang-Baxter algebras in the conformal field theory. There exist many deep connections between these and ordinary differential equations. This was then extended to a massive quantum field theory, the Sine-Gordon model, in 2010. And very recently, just 5 years ago, in 2013, the ODI QFT correspondence was extended to a nonlinear sigma model, which is a two-parameter integrable deformation of the SU2 principal chiral field. And I'd just like to talk a little bit about this correspondence for this nonlinear sigma model in the simplest setting. And so the simplest setting that you could think, one of the simplest nonlinear sigma models I can think of is perhaps the O3 model. But in order to describe this ODI QFT correspondence for the O3 model, I'm actually going to need its one-parameter deformation that was proposed by Fatih, Onofrian, and Zamolodchikov. So here is the Lagrangian, and kappa here is the deformation parameter. Now when kappa goes to 0, you can sort of neglect this term in the denominator, and the Lagrangian just describes free fields restricted to lie in the 2 sphere. As kappa goes to 1, the sort of the target space where the fields live can be visualized as the long sausage with all the curvature concentrated at the tips of length proportional to the logarithm of 1 minus kappa, and for this reason this model is known as the 2D sausage model. We'll be considering this model in finite volume, so x lies in this interval, and we're going to impose this twisted boundary conditions with this twist parameter k. So now we've described the model, let's describe the ODE counterpart to it. And sort of the key ingredient on the ODE side of the correspondence is this sort of modified, so-called modified Sinch-Gordon equation defined on the punctured Riemann sphere with three punctures. Here, these are the parameters actually of the sausage model. So n is related to the Planck constant, whereas m here is the dynamically generated mass through the mechanism of dimensional transmutation.
So this is an equation that you get from a Hitchin system on a sphere. Is that right? Looks a lot like a Hitchin equation.
Well, I won't say the Hitchin system come from this historically, actually.
No.
This is something
that's fine, but
yeah,
which Hitchin system are we talking about? It's like SL2 with a regular singular point with some irregular singular point.
Well, anyway,
P is defining some spectral curve. It's certainly some kind of Hitchin system.
Yeah,
so the correspondence is between special solutions of this modified Sinch-Gordon equation, which have to have this sort of singular behavior at these punctures, and the eigenvalues of the quantum transfer matrices in the 2D sausage model. So, sorry?
What is the equation become in the limit when kappa goes to, when it becomes a sphere?
Well, that's actually very subtle. That's a difficult one to say. This is actually why we focus on the...
Actually, m goes to infinity with the limit of the spheres. Well, it's a difficult to, you know, the limit is not trivial, but in principle m goes to infinity, it's just the spheres.
I mean, that's the reason why we sort of study the sausage rather than the O3
ODE
signal.
you could describe.
It's sort of simpler on the ODE, yeah. So just to make this correspondence more precise, so this modified Sinch-Gordon equation is an integral partial differential equation. And in particular, it's sort of zero curvature representation. It's given here with the connection components are given by these expressions, where these are just the Pauli matrices. And so for a given eigenvalue of T at lambda, there's a corresponding solution of the modified Sinch-Gordon equation, such that the eigenvalue is expressed in terms of the connection coefficients of the auxiliary linear problem. So this relation is rather remarkable because it reduces the computation of the spectrum of T at lambda, which for the 2D sausage, we don't know how to do this, for example. We can't construct these operators, to a certain problem in the theory of classical integral partial differential equations. And here we have sort of the inverse scattering method and also the methods of classical analysis. So it sort of allows the computation of eigenvalues of T of lambda. It provides another way of computing, which otherwise would be impossible. So at the moment, as I was mentioning, the ODE-IQFT correspondence is sort of a conjecture, and it needs verifications. And it's not clear how to verify for the 2D sausage because, as I mentioned, we don't know how to compute the, we don't know how to construct the transfer matrices or to compute their spectrum independently of the ODE for the case of the 2D sausage. However, one can try to verify in the UV limit. And on the IQFT side, we have sort of the approach by Bozhanov, Lukyanov, and Zamolodchikov that allows us to construct sort of a representation of the Yang-Baxter algebras in the CFT and then to construct this quantum transfer matrix T, and including computing its spectrum.
So what conformal field theory is the UV limit we're talking?
We'll get to that. For the two, we'll discuss this. Whereas on the ODE side, there's a dramatic simplification of the differential equation, and the problem becomes a lot simpler. So I'm afraid Professor Moore's question is going to have to wait, because first we'll be discussing the UV limit of the ODE. And in this case, we sort of take this parameter m goes to 0, so then this term disappears, and we just get the Liouville equation. And as a consequence of this Liouville equation, this sort of combination is holomorphic, doesn't depend on Z bar. And in fact, for the vacuum, which is what we're going to be discussing in this presentation, the corresponding solution is given by this expression. Now, if you plug this into the matrix system and rewrite the matrix system as a second order differential equation, we end up with this sort of ODE, where P of Z is given by this expression and tau is given here.
See, what were Z1, Z2, and Z3? These are parameters in the sausage
So
model.
these are the punctures of the Riemann sphere.
I understand that, but in the relation to the sausage model?
So they can be taken to be anywhere by transformation. It doesn't matter. Okay.
So you can put them in 0, 1, and infinity?
Yeah, and it's, in fact, when we do computations, we don't use work with this one. We actually do put them to 0, 1, and infinity. We study that system instead. So how about the UV limit, going back to Professor Moore's question, how about the UV limit of the sausage? Well, the UV limit corresponds to when the parameter kappa tends to 1. In this case, the target manifold can be pictured as a long sausage, and in the when kappa equals to 1, it becomes two disjoint, half infinite Hamilton cigars. And the this means that the UV, the CFT underlying the UV fixed point, to answer Professor Moore's question, is this sort of cigar in LSM, which was also known as the Euclidean black hole. And the Lagrangian, I've written the Lagrangian here explicitly in coordinates, where phi sort of goes along this direction of the cigar, whereas this one goes around. And the boundary conditions that we had for the sausage model with this twist parameter k becomes these boundary conditions for the cigar. Now let's, in order to construct the transfer matrices, we'll obviously need to discuss the spaces, the Hilbert space for the quantum cigar. And the way this is done is we realize that the cigar has this sort of region where the target space is flat. And in this case, the equations of motion just become the wave equation, or the D'Alembert equations, whose solution can be written in terms of two arbitrary functions, two chiral fields. And we can take these chiral fields and express them in terms of their zero mode momenta and oscillators, and quantize these fields. If we let Fp1, P2 be the Fock space that's generated by these oscillators, labeled by the zero mode momenta P1 and P2, then the Hilbert space of the cigar is just this direct sum of all possible values of the zero modes. And we have obviously a holomorphic component and an anti-holomorphic component coming from plus and phi minus, alpha plus, alpha minus. Yes?
You said that the cigar model defines conformal field theory, right?
Yeah.
How can you see that from first principles? Doesn't this have curvature?
So how can you see?
So the cigar has curvature, non-zero curvature, right?
Yes, yes.
Ricci curvature?
So it definitely has non-zero curvature.
Yes, so isn't the beta function for this model?
The beta function is 0.
So, but how is that?
Okay, well, you have a dilettante.
Okay.
All right. Yes, and so this space of states, we're only going to focus on the holomorphic part, of course. And the space of states can be interpreted as scattering states, where P1 is sort of the incoming momentum of the string, and P2 is sort of the transverse momentum of the string. Now, how can we construct the quantum transfer matrices? Because this Cigar nonlinear sigma model has the same problem with non-ultra locality as all the other sigma models, and as the ON models and so on. But fortunately, in this case, the problem can be solved. So under a gauge transformation, where G is some matrix which could have whose entries could depend on the field, under a gauge transformation, the Poisson brackets are not invariant. And this raises the question, maybe we can choose a gauge transformation, be very clever, and find a gauge transformation such that in the new gauge, the connection has its ultralocal form. And this can be done for the two-dimensional sausage. And we found it in 2017. So now that we have this ultralocal gauge for the cigar, we can immediately, we have the scanning exchange relations, which we can quantize to the Yang-Baxter algebra. And using the BLZ approach, it's possible to construct its representation in the Hilbert space and to construct these quantum operators T of lambda, which act in the Fock space and which form a commuting family of operators.
What goes into finding the the suitable gauge? Like,
it's just brute force calculation. What do you mean?
I mean, is it like what's special about that gauge? Is it something simple or?
So when people found the connections for these models, it's usually sort of they find whichever connection is works, and they don't really worry about the gauge. Like when first people were studying, say, the principal chiral field, they had their own ideas and methods of how to construct a zero curvature representation, and they obtained some form of the connection, right? And this connection is non-ultralocal. And then we had to work hard and come up with a gauge transformation to make it ultralocal. And in fact, the form of this ultralocal connection is actually slightly more complicated. It also has an elegant expression, but you wouldn't be able to tell by looking at it that this is ultralocal, this is non-ultralocal, except maybe if I wrote it in explicit coordinates. But in terms of complexity, they look about the same.
But to solve for G, what do you have to do?
Well, it's sort of a brute force computation.
Yeah, but brute force, you're like solving differential equation, some linear system, or like what's
so
the
you
approach?
assume that G is it's some 2x2 matrix. The entries are given in terms of fields and their field derivatives. Then you do this transformation starting from the connection that you find in some previous, the usual connection that was found in the first place. You do this gauge transformation, you get some horrible expression. You compute the Poisson brackets, say by Mathematica. Well, this is an approach to use Mathematica. Then you look at the term proportion of delta prime, and you try to choose sort of the coefficients, I guess, to kill it.
And it happens to work out.
Yeah, I'm to be honest.
There are certain answers you just try to, but no guarantee. And actually, in this simple example, you can find Poisson gauge, but let's say for all 4 models, already you cannot find. Well, it probably doesn't exist. So a priori, it's not clear the situation what actually is still there.
Well, there is some mystery.
Yes, so that is something. Well, of course, all this you can find by the answers. Choose a certain answers and try to.
And that's for G.
And that's for G, right? But no systematic approach is unfortunately.
Yeah,
but maybe it's not necessary.
Yeah, so this was just a brute force calculation, many pages of stuff. Okay. So I said that we can use the BLZ approach to construct these operators, and then on the one hand we did field theory calculations, and the other we found ST of lambda, these eigenvalues from the ordinary differential equation side, and we found full agreement. So now if you accept the ODI-QFT correspondence for the sausage, then you can sort of compute these eigenvalues of the quantum transfer matrix. And this is what we, and the problem is reduced to some sort of problem in integrable partial differential equations, which can be handled by the inverse scattering method. And so sort of using this methods of classical analysis, you can get these eigenvalues. And this is what we did for the vacuum eigenvalue. And we reduced the problem down to these integral equations. Now they look very nasty. So these g's are sort of the known kernels. These epsilon and omegas are the unknown functions. The parameters of the sausage model, such as n, goes into these kernels. You can also see the dependence on the dynamically generated scale in this R here, and also the radius of the world sheet. And here is the twist parameter as well. So these are very sort of nasty looking equations, but despite this, they can sort of be solved on your laptop numerically in like 30 seconds. And then once you have these functions, omega and epsilon, you can sort of compute the transfer matrix very simply. There's a simple formula relating epsilon and omega to the vacuum eigenvalue of the transfer matrix. And that gives you information about all the sort of conserved quantities, at least the vacuum eigenvalues of all the conserved quantities in the field. So we derive these nonlinear integral equations, and now that we have this tool, let's discuss. Let's discuss some sort of physics. And let's sort of go away from these technicalities, and let's see if we can get extract some nice physics out of these equations. And let's consider the simplest model, the O3 model. And the O3 model is just the nonlinear integral equations describing the O3 model are just obtained by formally setting n goes to infinity in the nonlinear integral equation, and this can be done. And the O3 model, we should think back to Polyakov. So it was studied because it has a variety of very interesting quantum effects. In particular, it's asymptotically free. And so, for example, the characteristic of this is a negative beta function. Now, here mu depends is the scale, stands for the scale in this renormalization group equation. And in our case, since the only dimensional parameter is r, is the radius of the world sheet, is this radius, which is sort of identify mu with the inverse of r. So in other words, by putting the theory on some finite volume, we can sort of probe different length scales by changing the cylinder, changing the radius of the circumference of the cylinder. Now we know that the small r behavior, the theory is asymptotically free. So it's just a free field theory of two massless particles, bosons, and the corrections are perturbative in this running coupling constant. Now, in the large R behavior, we have sort of confinement, and we have free massive particles, and whose scattering was described in this work by Zamolodchikov and Zamolodchikov. These free massive particles form an O3 multiplet, and the scattering is just factorized and completely determined by two particle scatterings. Now, using the nonlinear integral equations, we computed sort of the finite volume energy. Now, this finite volume energy is sort of regularized. We subtracted an extensive part, so it goes to 0 as r goes to infinity. And here we've plotted it as a function of the running coupling constant f. So these dots come from the solution of the nonlinear integral equations with different values of the twist parameter. Okay. Now, for small, sort of in the high energy, where r is small, we have a theory, as we say, of free particles, and the corrections are given by this sort of perturbative expansion of the running coupling, which I've plotted by this sort of dotted line here. You can also see that this value here is actually negative 1/3, which is also what you'd expect for two massless bosons. Now, the large R behavior is determined by the scattering theory, and using sort of the S matrix from Zamolodchikov and Zamolodchikov's work, we computed the Lusher corrections that describe the large R behavior of the Casimir energy. And you can
try to understand the -1/3 why that's so obvious. So I should be thinking about C/12
Yeah,
C
so
is 2?
pi c on 6, right?
I see on 6, okay.
And we're dividing by pi here.
I see.
So it's minus 1/3. Yeah, so these are sort of your Lusher corrections, and you can see that they sort of fit this thing here. So this is also another confirmation that the ODI QFT correspondence works for the two-dimensional sausage model.
What's the Lusher formula?
It describes a large R behavior in terms of sort of a particle winding once around, a virtual particle going once around the cylinder, and then two virtual particles with the possibility of them scattering. Sort of there's a
But it's not exact,
expansion.
obviously.
Well, it's for larger. It's an asymptotic. No, it breaks down when R gives. Well, you need more and more. Oh,
Wait. Is it an asymptotic expansion?
it's asymptotic expansion.
In F? Sorry, asymptotic in F.
Yes.
Well, you're plotting things
In
in
R.
X,
In R. Well, asymptotic in R. Well, we're plotting as a function of it.
Okay.
These dots are exact if you believe sort of our formula, whereas these are sort of
Right, that's what I'm
asymptotics.
asking. So, is the discrepancy because you didn't go far enough in the preservative expansion from the Lusher formula?
We did second order.
Ah, so you stopped at a certain order.
So stop second order. Yeah, it's an asymptotic expansion. Yeah, of course. It's not an exact. Like the only way you can compute this exactly is using non-linear integral equations. At least for k is not equal to 0. Okay, so that's a nice physical result. So let me just conclude by just stating the main result of my dissertation. So I studied the quantization of nonlinear integral sigma models, and the first problem that you come up against is the problem of knowledge for locality, and obviously I spent a lot of time studying this problem. And for certain models, such as the 2D sausage, I found that you could bypass it using a gauge transformation. However, say for the O4 sigma model, for the SU2 principal chiral field, to the best of my knowledge, the gauge transformation doesn't exist, and I spent many sort of months trying to find it. However, that's still not that bad, because there's an alternative approach that was devised, and using this alternative approach, we showed that for the two-parameter deformation of the O4 model, known colloquially as the 3D sausage, the scattering exchange relations are there. We show that they exist in the UV limit. Then, of course, most of my research was based with the development of this sort of ODI QFT correspondence. And I studied on simple examples like the 2D sausage, the 3D sausage model, the integrable deformations of the SU2 principal chiral field, I mean. And I demonstrated its power by calculating quantities which you wouldn't be able to get in any other way. And some part that I didn't talk about in this presentation is the study of critical spin change systems, which is just very interesting from the point of view of integrability in condensed matter physics. And we used the ODI QFT correspondence to study them as well, in the scaling limit, of course. And of course, the ultimate goal of my work is I want to sort of develop these methods and apply them to nonlinear sigma models, which appear in realistic problems in high energy physics and condensed matter physics. And sort of the first steps in this direction would be, first of all, extending the approach to NLSM associated with higher rank Lie groups, such as the higher rank Lie groups and supergroups. And one particular model that's with respect to this, that's caught our attention is the Klimchuk model, which is a deformation of the principal chiral field for any group. Also, of course, in our work, we use the BLZ approach, we try to avoid the lattice as much as we possibly can. However, a lattice formulation is also a very useful thing, because it allows you to apply a wide range of numerical and analytic methods for the study of NLSM, and we think I think it's an important problem to devise a sort of lattice regularization for nonlinear signal models. And lastly, at the moment, the ODE IQFT approach is very good at computing sort of the spectrum, so the eigenvalues of T of lambda. It's very good for that. However, another interesting physical quantity are correlation functions, and it's important to see what these correlation functions are on the ODE side. And this is actually the work that I'm currently doing, well, currently at this moment. So thank you very much for your attention. Any questions? Yes, Professor.
So what about some calculation of things like entanglement entropy? Do you know how to diagonalize T of lambda? Does that help in entanglement entropy?
So T of lambda we can't actually construct up, but we can compute its eigenvalues. So you're asking about entanglement entropy. I mean,
maybe domain walls or things like that.
So we haven't been considering that.
So my other question was, as I mentioned, the ODE that you're looking at is a special case of what you can get from something called the Hitchin system. Mm-hmm. The integral equations you're studying, well, I don't know if they're the same, but very similar integral equations occur when you try and write down twistor coordinates for Hitchin systems. Mm-hmm. And so all of this is related to n equals 2 four-dimensional field theories. And I was wondering if you thought at all about that connection.
Yeah, I thought about, definitely thought about this sort of connection of integrability to supersymmetric gauge theories. But sort of at the moment I've been wholly engrossed in sort of developing these methods. But definitely when I finish, when I have some more spare time, I'll definitely look into them. I think that's very interesting.
Translate all you're doing in this stuff, because it's certainly they're certainly the same.
There's some striking similarities.
Absolutely, but it's still
But it's not clear that I'd love to be able to take the results and say something about four-dimensional n equals 2 field theories, and I wouldn't know how to do that.
So, can you say something about this preliminary results? And also, so you have just the crude sort of scheme. So you have a certain correspondence between eigenvalues and what of this ODEs?
Connection coefficients.
Connection coefficients?
So say for example, you have an ordinary differential equation.
Yes.
And say as an example, it's Fuchsian. And so it has some regular singular points. Or it could also have some regular singular points. But
does yours have irregular singular points?
Yeah, it does. Yes, it does.
So these are Stokes matrices?
Yes, I guess so. But the idea is that you have a basis of solutions at, say, one singular point, a basis of solutions at the other, and the connection coefficients are the things that relate these two bases. So it's a second-order differential equation, so you can rewrite one basis in terms of the other.
Okay.
And sort of those coefficients, that matrix,
yes,
contains your connection coefficients.
Okay, and eigenvalues are where?
And so the eigenvalues are expressed in terms of these by some very simple formulas.
And so now the norm of the eigenstates of the beta states, what would they correspond to?
Well,
they also have to do with these matrices, or?
So first of all, we don't really know, because we're doing this work right now. But there's a sort of Godin formula that expresses the norms in terms of the Yangian. The matrix of the determinant of the second derivatives of the Yangian. And we know how to, for example, express the Yangian in terms of an ordered differential equation. So that's sort of the lead that we're following. We don't know how to express the derivatives of the second derivatives.
So if you can express the Youngkin off-shell Young functional, then you're done, right? So, but you can do this, for example, on-shell or maybe matrix of the Hessian matrix of the second derivative, but on-shell. But if you can express it in terms of the out-shell, off-shell, then Google the correlation function of the norms and more completely. In principle, it looks like it's possible.
Okay. Oh, okay. So, maybe along the version.
Professor Bhajan, can you hear, or have we lost?
Yes, I'm still here.
Do you have any questions?
No questions. No
Okay.
questions.
Thank God.
Yeah, I'm here for no questions.
Say it again, sorry.
I said here, no questions.
No questions as well?
Yeah, no questions.
Okay. Oh, go ahead.
So as you said, in some cases you can get rid of the non-ultralocal Poisson brackets by doing the gauge transformation. In other cases you can't.
Yes. Well, we
So
weren't
otherwise
able to
you
find
think
it.
it doesn't exist. I mean, shouldn't there be a more gauge invariant classification of these integral models?
Yes, so this is sort of the big problem, right? These sort of connections are gauge invariant, and this sort of approach, the Kizom approach, requires sort of choosing the right gauge.
Yeah.
And sort of what we think is that maybe you can sort of somehow prove the scanning exchange relations without that step of having these ultralocal Poisson brackets. And that's what we're working towards, and at least in the UV limit where we think it's possible. However, you know, we don't know the answer, the full answer, of course.
Okay.
Yes.
Model, what do you use as your signature for confinement, and do you have a precise scale for when confinement sets in?
For the O3 model you're asking, what's the signature for confinement?
Yeah. And do you have a scale for when it sets in?
So I guess by confinement I mean the dynamical generation of the mass scale M, right? And what's the second question?
Do you have a scale for when it sets in? I mean, is the transition smooth or at one single point?
Is the transition smooth? I mean, I'm not sure what you mean by smooth. There's certainly like no phase. There's certainly nothing like blowing up or you know, breaking down, like at least from this point.
So is this a screening of the ON charge for the O3 charge?
So you're asking at what point in this diagram you have confinement, right? I guess it's smooth. It's just smooth transition.
This is finite size, right?
This is infinite volume, yes.
So this wouldn't have any sort of singularities or stuff.
No,
Any phase
no,
transitions.
no, because yeah, well, no. further
Okay,
questions?
so
Thank you very much for your attention. I have food. I'll bring it out in a second. And there's also beer and wine. And I hope to meet you all there. And hopefully there's enough stuff so we can go there. And I guess we should leave the committee alone. That's it. I'll just leave the Skype here, right? I'll leave this setup. Thank you all for coming.
I know the terms don't make any connection.
I understand that the wiring things improves your things for the same.
Мы пока хорошо, перевести сейчас.
That was it.
I would say that I'm very happy with this. Not maybe not my, the presentation stuff, but how he worked. He's actually very well. He actually
Presentation was excellent.
yes, presentation was
you
good
see,
too.
he's
His presentation was better than your talks, okay?
yeah, but you see, he's
Put it straight.
maybe not well so good educated, and he know nothing about the kitchen system stuff like this. But you know how he works. I actually impressed. But I think he's very good. And but he did, of course. And I'm very disappointed he leave. But I don't know how to do it.
Where is he going?
Hmm?
After this, I mean, what is he doing?
He will go to Daisy.
Daisy?
Daisy, right?
Ah,
Yeah. So
Because what is
yeah,
Daisy?
Daisy it's a gamble. Yeah.
They do a lot of the equals 4 and equals 2.
Yeah, I hope he. I
He's
hope,
not going to be able to get away from it.
Yeah, I hope he will learn about more. But what?
Well, it depends on whether he talks to Teschner or Schomerus.
Yes, yes,
If he
yes.
talks to Schomerus, he won't do that. If he talks to Teschner, he will.
Yeah, yes. And
They're both at Daisy, so he has a choice.
Okay, I mean, I think this is great
This is,
work,
this is,
so
this
there's
is,
no
this is
issue.
obvious, yeah, so.
all right. Okay. So I need to bring the.
We need to sign something, right?
Yeah.
Are you on the next one? I have another committee on Monday.
I don't think
You're
so.
not on that one?
Yeah, I think this is my last one for this semester.
How many have you done this semester?
Not that many. Two.
Just the external members.
Yeah, I'm sure that they're gonna say yes.
Volodya, do you hear me? Do you hear me? Volodya. Volodya, do you hear me? Well, привет. So what's your opinion? So what can you say about? Is there anything to say about his talk and about his work? And you know, since you're external, did. Wow. Володя?
Who is on Monday? Who's student?
Mine.
Oh, your student.
Daniel
Okay.
Brennan.
Oh, I see, okay.
So, that's the last one, final.
Okay.
It's 4.
Oh.
So, do you work on integrable things?
Yes.
Yeah.
Yes, I do a lot of that, yeah.
Integrable spin change, though.
spin chains, lattice models, not permanent content.
Давайте я камеру выключу. No.
So I'll just.
But still, a committee member should at least.
I just want to get rid of this because otherwise